Okay, 10th grade, here's your lesson number 2, energy and chemical reactions, our first real kind of full lesson for this unit. So we're going to review some stuff you should know from grade 9, but are really key ideas for this course, for this unit. And then we'll be learning some new stuff and doing some practice calculations. So you will need your calculators for today's lesson. Okay, so here's your template for today. It's a 2-pager. So you'll notice the first page we have space to do 2 diagrams. One here, about coefficient changes, and then here is for a formula. So maybe a little less space for that, but it's a formula, not an actual drawing. And practice calculations, you're probably not going to have enough space to do all your calculations on that half a second page, but you can definitely start there and do the ones we're going to do together, and then do the ones that are kind of homework on a separate page. So pause the video, copy your template down, please. If you're doing digital notes, you need to still do your calculations by hand, so you have to show me your work. So you're going to start uploading them with pictures, incorporating into your notes somehow, but you have to show me your calculations done by hand, okay? If you want to do them digitally with on an iPad or some sort of pencil, like how I'm going to do mine today, you can do it that way, but I have to see you actually doing the work, okay? Just typing the answers is not sufficient. Okay, so let's start with physical and chemical changes. This is something that you should have already heard, but I know we have students from different backgrounds in science, so we're just going to review this idea here. So, physical properties of matter. Physical properties are the properties that do not require to be changed, right? So you can observe these properties of matter, of a compound, of an element, of whatever it happens to be, without actually changing the matter. So we're not changing the density. So examples of physical properties would be the density, solubility, conductivity, malleability. So how malleability is how bendy a substance is, it can bend without being broken. How density is, can it conduct electricity? Is it soluble? Can you dissolve it in water or not? Those are all good physical properties. And physical properties are connected to physical changes. So physical changes are ones that you can do with the matter's going to change form, but not the chemical identity. So a good example of this would be changes of state. So example we have in the image here, melting ice. When you have solid water and you have liquid water, but still water, it's still 2 hydrogens bonded to an oxygen. It doesn't change identity, it's just changed its state. It's a physical property, it's a state of matter. Okay, so dissolving sugar in water, is that a physical change? Why? It's definitely a physical change, and the reason why is because the sugar still retains its properties when it's in the water. So if I dissolve sugar in water and I drink that sugar water, it tastes sweet. That property of the sugar to be sweet hasn't been lost. And I can reverse this change. How can I reverse the change of dissolving sugar in water? Well, one thing I can do is I can boil the water away slowly so only the sugar is left. And then I can still separate them back together again. What are some other examples of physical changes? Well, of course, changes of state. We have anything where we're changing the size and shape of something is a physical change. Any sort of dissolving, combining a mixture together. Like if you think about chromatographic markers, where you're mixing different inks together, if you can then separate them physically, that is a physical change. So just a reminder of this, you don't have to draw this, you should already know this, but I want to make sure we have these words correct. So the processes, how we change states. Okay, I assume everybody's got melting from solid to liquid and freezing from liquid to solid. Condensation from gas to liquid, and evaporation from liquid to gas. These are the ones a lot of students don't remember, especially if English is your native language. We're going from sublimation, it's from solid to gas, and then deposition is from gas to solid. So write that down, whatever ones these you don't know, so you have it in your notes about physical change. States of matter are physical changes. These are particular examples. Okay, let's talk about chemical changes. So chemical changes and chemical properties are linked, just like physical changes and physical properties are linked. So what are chemical properties of matter? Do you remember that from previous chemistry course? Well, chemical properties are ones that you can only observe through changing the matter, through a chemical reaction. So we change the method identity, that's what we have to do to see a chemical property, and we can't change it back. So good examples would be reactivity. You mix vinegar and baking soda, it's going to cause a reaction. You have now lost that vinegar and baking soda, so different substances have been produced, including carbon dioxide. Flammability, you burn wood, you can't unburn the wood, you can't bring it back to what it was before. Acidity, that reaction between acids, is also an example of a chemical property. So that's a chemical property. A chemical change is a change in which the particles of a substance are rearranged and they make a new substance. So instead of being wood, as it was before, like cellulose, now it's changed into coal, or charcoal. It's a different substance, different chemical properties than it had before. A really good way to double check is something a chemical or physical change is just to think about, can you change it back or not? So for example, let's go with rust. Rust is a corrosion process. So if I have some metal and it's rusted, can I get the metal back once it's been rusted off? No, you can't. It's a corrosion reaction. It's oxidized with oxygen in the air, and now that rust is gone. You can scrape the rust off, but you're losing that metal. I have the metal still underneath, but it's gone. You can't reverse it. Okay, so this we can write down in the first box is this list I'm going to give you of the signs of a chemical change. So we'll be looking at different examples of reactions a lot in this unit, and you need to check, is it a physical change or a chemical change? So if you see one or more of the following signs, it's a good hint that it's probably a chemical change, but not a guarantee. Okay, so a color change. If it changes colors, for example, if we have a red substance and it becomes clear, that's a color change. Now, if I have a red substance and a blue substance and I mix them together and it becomes purple, is that a color change? No, because red and blue make purple when you mix them together, right? Think about your art class, color wheel, all that kind of stuff. Be careful. Color change has to be a color that's a new created compound, not just a mix of two previous colors. A change in temperature. Now this one is bolded because we're focusing on energy in this. So change in temperature is a really good sign of a chemical reaction. Either temperature has increased or decreased. Some sort of change means there's a chemical reaction definitely happened. If there's light produced, sign of chemical reaction, chemical change. If there's gas or an odor produced, sometimes you can see bubbles of gas. Sometimes you can't see that. You can smell an odor. It's also a form of gas. If there's a precipitate form, so precipitate is when you get a very fine solid being produced when you mix two liquids together. Usually if you let it settle, it'll sink to the bottom of a test tube. It looks like kind of a little chunk at the bottom of a test tube of solid that comes from mixing two liquids. And the biggest one is it difficult to reverse? If you can't reverse it easily without doing another chemical reaction, then it is probably a chemical change. So we're going to look at a little video clip of a reaction here, of a change. And you need to decide if it's chemical or physical, and which of those hints, those signs of chemical change, tell you it's chemical if that's what you think it is, or which ones are missing. So notice I've got two liquids, one in the test tube and one in the dropper. I'm going to drop it in slow motion. So two clear liquids. Come on, drop. Boom. Is this chemical or physical? And what are the things that tell you that? Well, this is definitely a chemical change. And I can tell because first we'll have a color change, a very cool color change. I have two clear liquids becoming bright yellow. Okay, there's a precipitate form. That yellow is actually a solid. It's where you mix the two liquids together, and so it's sinking down the bottom. It's being kind of mixed up because the drop's falling down, but if you leave it, it will all sink at the bottom of that test tube. And that's so difficult to reverse. Now we can't see temperature change or gas or odor in this video, but I have 2 or 3 signs that prove this is a chemical change. Okay, so take a minute now and go to your big ideas page. Our first big idea we are starting today. How does the conservation of energy within systems explain the processes of chemical reactions? So we'll be talking about this over the next few lessons all week this week, so make sure that you kind of start writing this today and you'll finish by the end of the week. A lot of big ideas in the student are kind of overlapping ideas. Okay, so you need to draw this diagram here, both of them. Make sure you draw the delta H and the arrows right directions, okay? Well, that'll be more important as time goes on. So when chemicals react, these reactions cause energy changes. And can you think of any examples of energy changes caused by a chemical reaction? Well, a good example I always think about is those little hot pads. If you've ever looked at somewhere really cold, you can get these instant heating pads for your hands and for your shoes. You can kind of break them open and it instantly reacts and produces heat. They're wonderful for like outdoor concerts and New Year's Eve, that kind of stuff. No, I missed a typo. Energy changes. Look at that, 2 typos. So that's a good example. A really good example is temperature. Changes in temperature, especially when you have heat produced, is a really good example. Or combustion, if you're burning something, whether it's fossil fuels, whether it's wood, whatever it happens to be you're burning, that's a clear combustion reaction. It's definitely going to be producing heat. So the way to kind of think about energy in chemical reactions is to think about the bonds, because the bonds are what's changing in chemical reactions, being broken and new ones being made, and bonds change energy. So changes in bonds affects the energy of a reaction. Most reactions are ones in which the energy is transferred to the surroundings. So here we have energy from inside the system of the reaction, and it's moving out to the surroundings. That's an exothermic reaction. Okay, and then in an endothermic reaction, what is happening there? Well, the clear diagram right there, where we have energy is going to decrease in the system and come from the surroundings into. Remember, the energy has to come from somewhere. Energy just appeared, has to come from somewhere. So in exothermic, energy is coming from the system going out. In endothermic, it's going from the surroundings into the system. A good way to think about that, of exothermic and endothermic, as being a positive or a negative change in energy. Okay, so which of those 2 reaction types is a positive change in energy and which is a negative, and why do you think that's the case? Well, exothermic is definitely a positive change in energy. The energy is moving out, it's changing the environment around it, and endothermic is therefore negative, it's decreasing in temperature. Okay, they release it. A good example of an exothermic reaction is magnesium ribbon and hydrochloric acid. So here I have magnesium ribbon and HCl, and the temperature here is going to go down. So it's going to go up, a higher temperature being produced by the reaction between these 2 reactants. And endothermic are the negative energy changes. They take in the energy from the surroundings, from the environment. So here we have sodium hydrochloric carbonate, and we have hydrochloric acid again, and the temperature is going down in this case. Now notice in both of these diagrams, they're in styrofoam cups. Why would I have to put my chemical reactant in a styrofoam cup? Let's smart a beaker. We use beakers most of the time for chemical reactions or a test tube. Why are we doing this in styrofoam cups? Well, styrofoam is a good insulator, so whatever temperature is going to happen, it should stay within the cup, and it'll be easier to tell the change in the system without it being affected by the environment as much. So the change can only happen kind of up and with the air, not on all sides like it would if it wasn't in a good insulating vessel like a styrofoam cup. Okay, so remember, energy cannot be created or destroyed. There's a fundamental law of nature called the law of conservation of energy, and every branch of science knows this. We talk about it in biology with photosynthesis, light energy becoming chemical energy, and then we talk about different kinds of bonds being broken and made to get energy. That's all chemical energy changing forms. Energy has to come from somewhere, and that's very key in chemistry, physics, and everything. That being the case, energy often changes form, right? It doesn't just stay as one kind of energy, it often changes form. So what forms of energy are really common to chemistry? We looked at a lot of different ones in our physics unit, but now we're in chemistry. So what kinds of energy are common in chemistry? A good example of potential energy, particularly in chemical bonds and in the nuclei of atoms. So nuclear energy is potential energy that's been released from the nucleus of atoms. Kinetic energy is another really important one, and that's the energy of the particles, right? So a good way to kind of think of it is thermal energy is the kinetic energy of all the particles in that substance. Okay, so temperature, what temperature really is a measure of the average kinetic energy of all the particles in that substance. We're talking about endothermic and exothermic. That temperature change is really a change in kinetic energy. If it's cooling down, it has less kinetic energy. If it's heating up, it has more kinetic energy. So if you look here, we have different with the particles moving. So just because we can't see these particles, they're moving, they're not moving. So particle theory tells us about movement of particles. The higher the temperature is, the more the particles are moving. Okay, now this is kind of the same diagram from the last page, just blown up a little bit here. We need to think about what happens when different energy systems are coming into contact with one another. So when there's two systems of different temperatures, so high temperature, low temperature system here, maybe you have some warm air just blowing off a heater in your house in the wintertime, and you have the regular cold air coming from the window. When those two systems of air particles meet, there's going to be a thermal energy transfer between them. And that will continue until it reaches thermal equilibrium. Okay, we have a net heat transfer, everything is at equal temperature, then it will stop. So these particles will be a lot more than these ones, and then through collisions with the particles, those stars are collisions, it's going to transfer that thermal energy from the high temperature to the low temperature. So this idea of having a gradient, an equilibrium you're trying to reach, is very common in natural systems. We talked about it with concentration, we talked about it with pressure, with breathing, with concentration, with diffusion, all those kinds of things. And this with heat, with thermal energy or kinetic energy, it's called heat transfer. So the heat will transfer between high to low until everything is in equilibrium and the same temperature throughout. Okay, so let's talk about specific heat capacity. So here's the formula for this. I will show that in the box and write down what the symbols all mean. Okay, I put mass in grams. I removed a word there. We'll talk about more about that later on next lesson, but for now, just leave it as it is. So heat capacity is the amount of thermal energy, remember thermal energy is kinetic energy of the particles of a system, needed to change the temperature by 1 degree. And this property, the heat capacity of a substance, depends on a couple things. It depends on the material itself. Different materials have different heat capacities based on the way that particles are arranged in them, which elements there are, a whole bunch of factors, and the mass of that substance as well. The specific heat capacity, or C, that's the heat capacity per unit mass. So it's a universal measure for a particular substance. And it's really useful in that way because it allows you to always look at, compare substances directly regardless of their mass. It's per unit mass, per gram in this case. So based on this formula here, what relationships can you infer about heat capacity, which is C, specific heat capacity, and these other units? We talked about breaking down formulas and looking at relationships back in our physics unit, and we're seeing it again here. So what do you see? Well, you can see the energy is directly proportional to mass, heat capacity, and change in temperature. So as mass increases, so will energy. As heat capacity, specific heat capacity increases, so will energy. As change in temperature increases, so will energy. But they're all proportional. There's nothing being divided. It's a pretty straightforward formula. So take a look at this table. Here we have some samples of different heat capacities, joules per gram per Kelvin. Kelvin is a measure of temperature if you're not familiar with it. And I have liquid water, solid aluminum, solid iron, solid copper, and solid gold. And here's our specific heat capacities. So which of those materials do you think would heat up the quickest and why? Well, the one to heat up the slowest is going to be liquid water because that's how much joules of energy it takes to heat liquid water 1 gram up by 1 degree Kelvin. 4.18 joules per gram of water to heat it by 1 degree Kelvin. So which one will heat the quickest of all these different materials? There we go. Then we go with the lowest heat capacity, which is gold. Gold would heat up the quickest. So the least amount of energy required to heat it up by 1 gram of gold by 1 degree Kelvin. So if you were going to cook, let's say you were a chef and you had a restaurant with really quick turnaround time, but you had an endless budget, and you could pick any of these pans. You could pick any material to make your pan. You had a choice of aluminum, iron, copper, or gold. Which one would you pick and why? Well, if you want the fastest one, you're going to go with gold, right? Gold has the lowest heat capacity. It's going to heat it the quickest. But a lot of time for cooking too, we don't use gold because we don't, first of all, it's really expensive. Second of all, it's a soft metal. And third of all, we don't want things to heat up too quickly. We want it to be quick enough that gives an even heating. If the bottom part of the pan gets hot too quickly, stuff from the top part of the pan will burn, right? If you ever had trying to make eggs or a grilled cheese sandwich, it's easy to burn one side, or pancakes or crepes, and leave the outside uncooked, especially if it heats up really quickly. Okay, so let's practice this. So here's your formula. We have 3 practice problems to do. 1, 2, 3. Pause the video and count them. Here are the answers. If you get them right, then you can skip my explanation to the next slides. If you don't, then I'm going to go through each one for you. So pause the video, do the calculations, make sure you write the formula, substitution, and answer with units, just like we did in our physics unit. You still have to do all your calculations. Okay, so if you didn't get number 1 right, I'm going to go ahead and do it for you now. So I'm going to try and use my stylus on my iPad, so let's see how well this works, guys. So I have a mass of 1.5 kilograms, and I have a delta T of 7 degrees. That's not bad. And my specific heat capacity is 750. So how much energy is being transferred? Well, I have my formula, Q equals mc delta T. I have to always write my formula. And then I'm going to take my values, substitute them. So it's going to be hard to fit with the units. You guys should put the units, but my iPad is too small to do this properly. So 1.5 times 750 times 7. So Q is going to be 7,875 joules. Okay, that's the first one. Now, if you got the second one incorrect, here's the answer for the second one. So this case, I'm going to have a mass of 2 kilograms of water. My delta T is 25 degrees Celsius. My heat capacity is 4,181 joules per kilogram degrees Celsius. How much energy? So formula, Q equals mc delta T. Put my values in, and again, you should put the units, but I'm not going to because I don't have space in my little tiny iPad to write this small enough. So I have 2 kilograms, I have 4,181, and I have 25. Oh, it's not gonna fit. 25. Let's try to make this smaller. Okay, we can do this. 2 times 4,181 times 25. Hey! So Q is 209,050 joules. Okay, number 3, I have the energy given, so I have my Q is 46.7 joules. My delta T is 15 degrees Celsius. My specific heat capacity is 6,934 joules per kilogram degrees Celsius. So this time I have to rearrange my formula. So I have my Q equals mc delta T. but this time I'm looking for mass. So what you can do is you can rearrange the formula where mass is equal to C delta T divided by Q. And then just put your values in. So I'm going to write a space. 6,934 times 15. Oh, I messed this up, guys. Look what just happened. Okay, so I'm going to rearrange this formula. Focusing too much on using this iPad thing properly. What I'm going to get is I'm going to get M is equal to C delta T divided by, no, I'm doing it again. Okay. M is equal to Q divided by C delta T. There we go. That took way too long. So I'm going to divide my 46.7 divided by my C delta T, which is 10,000, 104,010, which is my final answer of this value up here in kilograms. Sorry guys, I'm trying to focus so much on making this numbers fit, which just still looks horrible, but hopefully that helped you guys understand if you didn't get that one on your own. So your homework is to do at least 10 practice questions. Okay. Now in the practice sheet I uploaded, we did the first 2 easy ones and the first medium one. You have to do at least 5 of the medium ones. One question is the table. You could do the whole table, or you could do 5 calculations of word problem ones. And the other 5 can be easy, they can be hard, it's up to you. If you're somebody who's really good at this stuff, try some of the hard ones. They involve things like converting units and other kind of more complicated things to do. Okay, so make sure when you put your question in your notebook, you say this is an easy number 2, or this is easy number 5, medium number 3, so I know which ones to check your answers when I'm checking your homework later on. Okay, hope this helped for you. I'll try and get better at using the iPad, obviously, but I really want a regular full-size iPad with this Apple Pencil so I can actually do this well, but my iPad mini will have to do for now. Alright guys, have a good day and take care. Hope this is helpful for you.